In this video, I'm going to look at equilibrium in industry, specifically equilibrium in the Harbour process and equilibrium in the contact process. So the Harbour process itself is the process by which ammonia is produced. Ammonia then gets used to go on and make fertilizers, massive industry, amongst other things. But in this video, we're just concerned with the equilibrium process here. So we know it's a reversible reaction. We've got a system that's set up in equilibrium. There's an iron catalyst that's used in the reaction to speed up the process of reaching equilibrium. So in the Haber process, the nitrogen just comes from the air and hydrogen comes from natural gas, that's methane, and they react in a 1:3 ratio. The gases come in and are cooled down. They react over an iron catalyst. What we need to do is we need to look at, in this video, what we're going to look at is what conditions favour the production of ammonia to give the highest yield of ammonia. So looking at temperature to start with, we know that forward reaction there is exothermic because the delta H is negative, minus 92 kilojoules per mole. So if I increase the temperature there of this reaction system, this closed system, by Le Chatelier, the system is going to try and cool down, so it will favour the backwards reaction. Okay, so for an equilibrium point of view, we want a low temperature because a low temperature favours NH3 production, ammonia production. So then in terms of pressure, we know that on the left hand side we've got 4 moles of gas particles here. On the right hand side we've only got 2. So ideally for this system what we want is high pressure, because if we put a higher pressure upon this system, the system tries to reduce the pressure by favouring the reaction that produces the fewest number of particles. So it will favour the forward reaction here. So high pressure favours the production of ammonia. Now because this is on a massive scale, this reaction is carried out on a massive scale, we know that there might be a problem in the equilibrium process. If we have a low temperature, the problem there is we get a very slow reaction. And as this is an industrial process, the slow reaction isn't good for us. In terms of pressure, what's the problem with high pressure? In industry, high pressure is dangerous, but also expensive. So we have problems here. While low temperature and high pressure favour a position of equilibrium shifted to the right, low temperature is just too slow and high pressure is dangerous and expensive. So compromises are reached. And the compromise conditions are around 500 degrees Celsius for temperature. That will increase the speed of the reaction. 200 atmospheres pressure, which is high but not too high. And an iron catalyst is used just to speed up that reaction as well. It speeds up the process at which equilibrium is reached. So with this reaction, as they're all gases that are used, what happens is the gases enter the reacting vessel, ammonia gets produced under the conditions, but when you cool down the gases, ammonia will reach a liquid stage first because it's got the highest boiling point. So the ammonia is just tapped off as a liquid then, and the other gases are literally just circulated back throughout the system, and it goes in a continuous loop. Now we're going to look at the other industrial process, just the contact process. The first step with the contact process is sulfur is just burnt in air. Our iron sulfide taken from the earth is burnt in air to create sulfur dioxide. So when we have sulfur dioxide, we react that with oxygen to form sulfur trioxide. Balance the equation there. The enthalpy change for that reaction is 196 kilojoules per mole. So again, we're going to look at temperature and pressure, what conditions are best favoured. I might add that in this process, vanadium oxide, or vanadium pentoxide, is used as a catalyst, reaches equilibrium quicker. So with temperature, we know that the forward reaction is exothermic, so therefore ideal temperature equals low, but we can say straight away that we know that this is going to be too slow, so the rate of reaction will be too slow there. And for pressure then, we're going to look at pressure next. And with pressure, we know that on this side of the equation we've got 3 moles of particles, here we've got 2, so ideally we want a high pressure, But we know again that's going to be expensive. As it turns out, in this process, this equilibrium process, the conditions used are again a compromise, and it's around 450 degrees C and atmospheric pressure. So that's 1 atm. And the vanadium pentoxide catalyst. The last step in this reaction actually is you take SO3. Ideally you just react it with water and you get H2SO4. Problem with this is if you react the gas SO3, sulfur trioxide, and dissolve it in water straight away, you get this sulfuric acid which actually becomes a bit of a fog, an uncontrollable fog, extremely corrosive. So what actually they do in industry is they just take SO3 and they dissolve it in pre-made sulfuric acid. This is what they do in industry now to get H2S2O7, and then when they dissolve that in water you get sulfuric acid from that. So this substance here is known as oleum. So that's a closer look at equilibrium in industry, specifically the Harbour process and the contact process. And we know from looking at this that compromises in the conditions have to be made in order to get a decent yield and safe working conditions.